This session is going to be about swarm intelligence. So, swarm intelligence basically refers to uh, intelligence of a swarm of animals or insects or birds or plants, okay, together. So, what happens is that it's like you have a collection of simple agents which sort of interact with each other, and they are able to produce a complex output basically. Okay, so they follow only simple rules, each of the agents, or you can say each of the um, individuals in the swarm follow some simple rules, and there is no centralized manipulation. But still, you find that when all this behavior of the individuals are combined together, you get some type of intelligent global behavior. So it is found to be doing what is known as emergence. Okay, so there is emergence of some global behavior. So some examples of biological examples of swarm intelligence are like ant colonies, animal herding, bird flocking, bacterial growth, fish schooling, etc. You have cases of building very complex nests by by agents doing simple things. For example, like termites. So they build a very complex nest, and the nest. I think each individual does not know. They know only their own job which they need to do, basically. So here are some examples of some swarm inspired algorithms. So whatever you find in biological systems is taken, and that is actually used, and you get algorithms which are used. So you have things like artificial immune systems, particle swarm optimization, ant colony optimization. So it started right in the 1980s actually, all these type of algorithms. So you have fish algorithm, artificial bee colony, uh, monkey search. So you can see there are a whole lot of swarm inspired algorithms, firefly algorithm, bat algorithm. So some of them, eagle strategy, etc. Right? So what you find is that there are a whole lot of algorithms. We'll just study one or two of these algorithms basically. So how does the swarm behavior? Let's see how it is and how we can make use of it. So you have something like flocking of birds. So you have birds which are going up in the sky. So they are all flying together. Okay, and you can see that there is a certain formation which is there, and that formation continues in that way, and you find that even the distance between birds in the flock also is sort of maintained, right? So how that is done, you need to see. Secondly, what is called the shoaling or schooling of fish. So you find fish going in the water in the same way, right? So there's a formation which is there, and you have a whole. It's called a shoal or a school of fish. So they all go together in a particular formation. Then you have the swarm behavior for algae. Okay. Um, then you have ants. So what these ants do is they make colonies. So you find that you have ant colonies, and in these colonies you find that each individual has their own job which they need to do in that colony. Okay, you may be a worker ant, okay, or you may be a food foraging ant, etc. So whatever is your job, you have to carry out. Okay, and what you find is, even though each ant has its own individual goal, so as a community they have a different goal, so all together they combine to carry out a particular goal. Then you have the leaf cutter ants, which search for large leaves, and they build bridge and highway. In other words, they build some type of passage where they can go through. Then you have the weaver ants, which build their nest by larval silk. Okay, so the silk which comes from the larva, and they form big chains using their bodies to pull the big leaves. Okay, so the big leaves, it will be very difficult for the weaver ants to pull, but they make use of their bodies and they pull them and they join them together by using the larval silk. So what you find is that you have a collective behavior, but the collective behavior is as a result of decentralized, self-organized systems. So you have many small individuals which actually combine together to form the overall collective behavior. So what you find is you get a complex behavior made out of the simple actions of individuals. So we can see here you have the nest which is built. This is the termite's nest. So you can see that each individual termite will not be able to do this, right? But when the whole swarm combines together and each termite does their job, it all combines together to form a complex system. So here are some examples of this. Okay, so this is the shoal of fish which you get, right? So they are going in the water, and then you have the flocking of birds. So they have a certain formation and they fly through the sky in the same formation, right? So nest building behavior of wasps and termite, flocking and schooling of birds and fish, hunting behavior of lionesses. So here what happens is you have a group of lionesses who together carry out the hunting behavior, and there is no communication between them, but still they know how to go about the entire hunting which is done, which is a totally complex maneuver altogether, right? So then you have group foraging and clustering of ants. So they go foraging for food, and then when one ant finds some food, you find all the ants are going in that same direction, right? So how does that happen? Then you have ant colony optimization, which is based on this foraging behavior of ants. And we have the particle swarm optimization, which is based on the flocking of birds. Okay, so that is used in the particle swarm optimization. So these are the two algorithms we are going to basically see. So you can see here you have the leaf cutter ants which I spoke of, right? So the leaf cutter ant actually use big leaves, right? And they come and they combine all those leaves together to form a sort of highway. And here you have the weaver ants. So you can see they use also big leaves and they combine it together and stitch them together by using their larva. Okay, and they actually use their bodies to move the leaves because they are so big, right? So if you take ants, okay, you find that there are more than two types of workers. Okay, so you basically you have what are called the minor workers and the major workers. So they each have different type of task. So you find that the major workers actually go and they bring the prey or they forage for food, all those type of things. They are much bigger in size, right? And you have the minor workers which stay in the nest and they feed the brood or clean the nest, etc. So you find you may find more type of workers, right? You may find workers who protect the nest. There may be foraging ants, there may be ants which feed the brood, etc. Right? So you find many types of ants basically. And if you take wasps, you have three categories. You have the pulp foragers, the water foragers, and the builders, right? So you can see that many of these insects have different types of insects which carry out different tasks. So if you look at termites is it's actually a very complex nest which they are building. So if you can see, you will see that you have cone-shaped outer walls with ribs, okay, with ventilation ducts from the base up to its summit, brood chambers in the center of the nest. Okay, and then you have something like horizontal lamellae supported by pillars, a base plate with spiral cooling vents, a royal chamber, which is a thick walled protection bunker, okay, fungus garden, okay, and there's a hole in the wall through which the workers can come in, and you have fungus garden is draped around the hive, and special galleries or combs lie between the inner hive and the outer wall for isolation. Peripheral galleries surround both above and below ground, which connect the mound to its foraging sites. Okay, so you can see how complex it is. It's like building a posh house. Okay, so you can see what all they do in the nest. But what you see here, you find that the if you take the individual termites, they will not be aware of what is going on, right? They have their own task which they do, and by the combining or the collective task of all the termites, you find that there's something which is complex, right, which is going on there. So is there any communication, etc., right? So the communication is actually, even if it is there, it's very minimal. In some swarm intelligence, there is some communication going on, but the communication is minimum, and there's no centralized system which actually manages the whole thing. Then you have the cuckoo bird which lays the egg and then it puts it into other birds' nests, okay, so that the other bird will protect the egg and see that the egg is laid, etc. So this is used in what is known as the cuckoo search. And then the flight mechanism is followed by what is called the levy flight. A levy flight is like a random walk, okay, where the step size has a levy tail distribution which is based on the cuckoo bird basically. So we have talked about enough of examples. So let us see what exactly happens here. First of all, the proximity principle is used. The population should be able to carry out simple space and time computation. So you have something like the center of the swarm. If you take things like flocking or schooling, etc., should be aware of where the center of the swarm is, and also your neighboring individual, and you have to follow, right? Quality principle, the population should be able to respond to quality factors. Principle of diverse response. Principle of stability, principle of adaptability. So all these principles have to be followed. So what are the three things followed by a flock, right? Move in the same direction as your neighbor. Remain close to your neighbor. Avoid collision with your neighbor, right? So these are three rules which are followed, okay? And behavior in social insects use all these things like self-organization, positive feedback, negative feedback, etc. So what happens is, one of the characteristics is called emergence. In other words, It's like some type of self organization. So they all combine together to do some complex task which is known as emergence. And then you have what is called stigmergy, which is the indirect coordination between agents. So when you have ants which are going to forage for food and then come back, it lays something, okay, on the what are called pheromones, and depending on the pheromones you have other ants going in the same direction. So this is an example of what is called stigmergy. That is, there's no direct communication between the ants. The communication is indirect. So it puts the pheromones on the ground, and then the other ant sees how much pheromone there is and then moves in that direction. Because you find the ants are very small, almost blind, memoryless, but they still can go as a group and forage. So this is how you can say it's a general framework for using the nature-inspired nature-inspired behavior and change it into an algorithm which can be used. Okay, so what are the advantages of this swarm intelligence? You find that the scalability, adaptability, collective robustness, individual simplicity, right? So you find that when you make use of these in the swarm intelligence, you find that it helps to get better algorithms. For example, the robustness, right? Because you are using a number of individuals, you find that it is robust, whatever you're getting, whatever you're getting from that. And there's some adaptability, okay, so changing according to the environment, scalability, etc. But you also have limitations. For example, it's not something which is not a time critical application. It's something which takes time, right? You can see that the emergent behavior will only happen when it keeps doing this iteratively, right? And it's only then that you're able to get a good solution. And then parameter tuning. There are a whole lot of parameters, right? So how do you tune those parameters? That's the problem. Okay, so for example, you have things like particle swarm optimization, which is based on the flocking of birds, and you have the ACO, ant colony optimization, based on the ants, and you find these are very it has a lot of tuning of parameters which needs to be, and it can lead to stagnation. So what you find is that you may find that the solutions, you have all the individual ants and each of them or individuals in your swarm, and each of them will be giving you a solution, and you may find that it sort of stagnates into just one solution. Okay, so then you find that there's no diversity, and therefore you are not getting the proper, you'll get what is called a suboptimal solution. So let us look at the ant colony optimization. Okay, so basically the ants, like I said, they put what is called the pheromone on the ground. Okay, they so the ants which pick the shortest route to the food will be the fastest to return to the nest, and therefore will reinforce this shortest route by depositing the pheromone on their way back to the nest, and this will attract other ants to follow the same thing. Okay, so for example, you find that this is the nest and this is the food, so you find they are going this way. Now if you put one barrier in between, you will find some of them go this way and some of them go this way, but after some time you will find all of them follow the shortest route from the food to the nest. So we can use this in the ACO algorithm. Okay. So this is the algorithm that you have. Represent the solution space by a graph. Okay. And each point, each vertex in your graph will be like an ant, right? Set the ACO parameters and initialize the pheromone trail, and then you have to generate ant solutions where the ant goes to the a point, to the food source or the goal point or whatever, right? And then you update the pheromone intensities and you keep doing this, okay, till there is some convergence or termination condition is met, basically. So what you are going to do is you are using this what is called the transition the state transition rule. Okay, so if it is at at node I, and it what it does, it sees all the different outgoing links, okay, from I, and then for each one you calculate this transition rule or the probability. Okay, this is the probability of the kth ant to move from node I to node j. So you use this and you get a probability. And what you do is, if there are say L, if you have say ni number of such ants or such paths, you find the path which has the highest probability and you move along that path. So that is the transition probability, and that transition depends on the pheromone. This is the pheromone tau ij, is the pheromone from the previous t at time, and then you have alpha and beta, which are actually constants. Okay, and this one actually is something which does not depend on the pheromones. Okay, some other knowledge about the system, if you want to put. Okay, it could be something like the distance or from this point to that point, or some such thing, right? So by using alpha and beta, you can actually decide how much importance you are giving to the pheromone part and how much importance you are giving to the other knowledge based information that you have, basically. Okay, so this is how we get to decide where the ant is going to move. Okay, so this nij beta is the heuristic value of the arc connecting I and j weighted by beta. Okay, this is a heuristic information which represents some a priori information that you have, basically. Okay, so if you use alpha and beta, okay, so high value for alpha means the pheromone information is given more importance, right? A low value of alpha makes the algorithm similar to a stochastic multi-greedy algorithm, right? So you use only maybe the distance between the two nodes. If you give say alpha, you give it a very low value. If alpha is equal to 0, it performs a typical stochastic greedy search algorithm. But if beta is equal to 0, only the pheromone information is used, basically. So once you do that, you update the pheromone. Okay. So what you are doing here is you're assuming some evaporation factor rho, right? And you are saying that this is reduced by the tau ij is reduced by that much, but you are also adding the delta tau ij, which is inversely proportional to the distance from the starting point to the goal. Okay, so if this is smaller, then you find that this value will be larger. Okay, so in other words, the pheromone value you're putting here will be larger if your uh, the the distance traveled is smaller. Okay, so what happens is more pheromone value is put along the links which which come in the path of the smallest path between the 2 points. Okay, so that is what is used over here. Another example we talk about is what is called the particle swarm optimization, which was introduced by Eberhardt and Kennedy, right, in 1995. So it's generally called PSO, and it's very popular actually, right? And you have lot of um, different problems which have been solved using PSO. So PSO draws inspiration from the sociological behavior associated with bird flocking, right? Okay, so birds have efficient social interaction that enables them to be capable of flying without collision, right? Scattering and quickly regrouping again and avoiding predators basically. Okay, so you're using the flocking of birds. Okay, so that is what is used over here. Okay, so how do you simulate the flocking behavior of birds? Okay, flock centering. Okay, flock members attempt to stay close to nearby flock mates by flying in a direction that keeps them closer to the centroid of the flock. Second one is collision avoidance. You avoid collision with your neighbors. Okay, and velocity matching. You have to match the velocity of your neighbor. Okay, so that you're going in the same direction and in the same speed. So flocking of birds. So let's look at PSO. What happens in PSO basically? Okay, you have particles. Okay, so it's something like you have a number of particles in the space, right? So you can look at it like if you have the n-dimensional space, you have the various random particles which you are choosing over here, and all these particles are going to move as you go on. So you may find that a best direction will be chosen and each of them will move in that direction, right? So what happens is as you keep going for a number of iterations, they'll all converge to one point which is supposed to be the best point, okay, the minimum or the maximum, whatever we are basically looking for in this n-dimensional space. So what we need to see is how these points move. Okay, so this is how they move basically. Okay, so if you take some particle, okay, say I, okay, so particle I in dimension d basically. So this is the velocity at time t plus 1 will be equal to the velocity at time t plus C1 is and C2 are constants, and R1 and R2 are some random values between 0 and 1. And then let us look at what these two values. Okay, so this is the best position of this particular individual eye. Okay, so you take the difference between that and the present position, and this is the global best that you have. So you take a difference between the global best of the entire swarm with the present position, right? And that will tell you what should be the velocity, and the new position of the individual eye will be the old position plus this velocity which you have calculated over here. So that's how you carry out. Okay. Uh, so PID represents the historically best position of the ith particle. Okay. And PGD represents the position of the swarm's best particle. Okay. Now R1 and R2 are random numbers between 0 and 1. C1 and C2 are basically constants, okay, positive constants that you have. Of course, you need to fix all these values. So here they are talking about fixing the value of C. High values of C1 and C2 can provide new position in relatively distant regions. Okay, so obviously you can't have C1 and C2 which are very large. Okay, so you need small values of C1 and C2, but if the values are too small, it may take a long time to reach the best position, right, which you are looking for. Then they say when C1 is greater than C2, you find it's biased towards the particle's experience. And if C1 is less than C2, then it's biased towards the swarm's globally best position, basically. Okay, so this is the particle swarm optimization. So what you say is that generally this term, that is the one which depends on the global best, is called the social part of the equation. Okay, and then we have the best of this particular individual, which is called the cognitive part of the equation. Okay, so these two together form the direction and the velocity in which you are going to move, basically. So this gives you your basic flow of the PSO algorithm. Initialize the swarm. You are going to initialize the swarm and evaluate the desired fitness function. Obviously, it is based on some evaluation of the points, right? So you are using the fitness function. And for each individual, you have to do all these things. Identify, update the swarm's globally best particle, update the velocity of all the particles, and move each particle to its new position. And you keep doing this, steps 2 to 6, right? Till some convergence or stopping criteria is met. So what are the strengths? It uses memory to store the particle's historically best position and the swarm's global best position. Okay. It usually has fast convergence, and also it's simple. It adapts to a changing environment, basically. Okay, so these are some of the strengths. Limitations. So you find that sometimes it's not able to locate multiple optima, right? So you can only get one optima in the thing, and also you may find, like I said, some type of stagnation also happening, right? So these are some limitations that we have, and you find that there is some similarity between PSO and GA, right? So you find both of them are initialized in the same way. So you find random particles in the problem space, and both use a fitness function. Both are nature inspired, because you can say GA is inspired by the neurons in the human brain, right? And both have lot of parameters which you have to tune. Okay, we saw just now PSO. We have C1, C2, R1, R2, etc. Whereas in the case of GA, you have things like population size, crossover mutation rates, etc. Okay, so there are a lot of things. Also things like swarm size, inertia weight, cognitive and social parameters, C1, C2, etc. So you find lot of parameters which need to be tuned. Some people use a hybrid approach where they use both PSO and GA. Okay, so you can do things like use PSO for a few iterations, then you use GA on whatever comes out of the PSO. feed it into the GA and use some iterations of GA, and that is fed into the PSO, etc. So there are a lot of variations in this. You can have GA PSO, you can have PSO GA. Okay. So in GA PSO, the GA population is used to initialize the PSO population, while in PSO GA, the PSO population is used to initialize GA population. Okay, so you find all these variations that you have. So that is even though there are a whole lot of swarm intelligence approach, we have just taken two approaches. One is the ant colony optimization, and second one is the particle swarm optimization, because these are two algorithms which are very popularly used. So we'll just study these two. So I'll close the session now.